So in Chapter 6, we're going to start looking at carbohydrates. And this is kind of our first foray into biochemistry or biological chemistry. We're going to look at the structure of carbohydrates and as well as some of their chemical and physical properties. So carbohydrates got their name because, well, they have carbon and they have components that looked from the chemical formula to be like water molecules. And so they don't really contain them. That's just the ratio that's in the formula. And so what we see for all carbohydrates is they have this kind of generic formula, C sub N, H2N, so twice as many hydrogens as they have carbons, and ON, where we have the same number of carbons and oxygens in a particular molecule. And we hear a lot about carbohydrates specifically with related to nutrition, and we're going to talk a little bit about that, but our main concern is going to be at this point about understanding the structural features of carbohydrates. We'll look more at how our body breaks down carbohydrates when we get into a later chapter. I think it's in 11 or 12. So there are simple and complex carbohydrates. And what we find is that when we have excess of carbs in the body, they're converted to fat. And so our body stores them that way until it needs the energy. Because basically our body will store anything that we consume that we don't use up because it's preparing for a time when it needs it and there's none available. And so the primary purpose of carbohydrates in our body, or one of the major purposes, is as an energy source. When we have carbs, we get energy from that, and that's great, and we need that. But there are also a couple of other things where they are found, and they're just as important there as well. One of which is in blood typing. So when we talk about being type A or type B or O, what we're referring to is the carbohydrate chain kind of attached to those molecules, and we'll look at some examples of that later on. Heparin is also a type of a carbohydrate. It prevents blood clots. And we also find carbohydrates either in DNA or in RNA. So when we're looking at carbohydrates, we can see we can have single carbohydrate molecules. We call these monosaccharides. We also see many disaccharides, which mean they have two of those saccharide molecules in there. A phrase we see less frequently, but particularly when we're dealing with blood typing groups, is oligosaccharides. So basically between 3 and 9 of those carbohydrate molecules connected in a chain. And then beyond that we get to polysaccharides. And a lot of times the oligosaccharides just get kind of jumbled in with the polysaccharides. And so things like starches, like we have a chain of glucose molecules, we'd have something that is a polysaccharide. And these can be quite huge, up to 10,000 of those in one chain. So when we're looking at the basic structure of our saccharides and these carbohydrates, and notice that we're using the phrase saccharide and carbohydrate interchangeably because they both actually mean the same thing. And so there's a couple of structural features we're going to look at, and this kind of represents how we're going to draw them. We always start up here at the top, we draw them kind of vertically, and we'll talk about why we do that later on when we start looking at what this kind of layout means. But what we notice here is that we have a chain of carbons down the middle, that every carbon has an oxygen attached. Now, all but one of them will have an OH group attached, and that remaining carbon will have a double bonded oxygen. Now, because the carbon with the double bonded oxygen is at the end of the chain, that makes this an aldehyde, but these others are all alcohol functional groups, and so this is where we get that CH2O or CnH2nOn template for these. If I were to go through and look at the number of carbons, I could say, well, carbons, there are 1, 2, 3, 4, 5, 6. Okay, they've already been counted for us. For hydrogens, I can go through and count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens here. And then when I look at my oxygens, I see that every carbon has one oxygen attached, so we have 6 oxygen. So we're following that template of the N, 2N, and N, and so we can kind of see where they get that carbohydrate, carbon with these water. But the waters are not truly water molecules attached to the molecule. That was just their initial assumption when they figured out what the empirical formula, what the chemical formulas were for these molecules. But we see that we don't have waters attached. One side has a hydrogen, and one side has an OH group. If it were going to be a water molecule, it would have to be attached as an H2O group, and we don't see that. So we have an OH and a hydrogen and all the carbons here in the middle, and then we have one of our carbons. In this case, it's going to be at the end. That makes it an aldehyde. But what we can also see is that carbonyl group, that double bonded oxygen, can happen not on the first carbon, but instead on the first or the second carbon. Now, theoretically, it could happen on one of the lower carbons, 3, 4, 5, in this example as well, but we're not going to worry about that. All the one examples we look at, the carbon will either be on carbon number 1, and we always start numbering these from the top to the bottom. The way we've drawn them represents the order, so you don't have to worry about going back, which way do I count. So we have carbon 1 up here at the top going to carbon 6. This is an aldehyde because we have our carbonyl on the first carbon, and remember, an aldehyde must have at least one hydrogen attached to the carbon, and therefore it must be on the end of a carbon chain. When I look at a ketone, remember that a carbonyl group here, C double bond O, we have a carbonyl, must be, to be a ketone, must be attached to 2 carbons. It can't have a hydrogen attached. And so we see we've got our carbon here and our carbon here, and so as a result, a ketone can never be on a terminal carbon at the end. It must be on a carbon somewhere in the middle of the chain. And so both of these are monosaccharides, and we can have a big variety of these carbohydrate molecules, some of which have aldehydes and some of which have ketones. Now, when we look at the chemical formula, we see that they're still going to have the same kind of template, even if it's a ketone. We still have our carbon. In this case, we have 5 carbons. When I look at my hydrogens, I see I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. And for my oxygens, 1, 2, 3, 4, 5. I still have 1 oxygen attached to every carbon. So I still have the N, 2N, and N kind of format for the number of each type of atom.